So today I will talk about the parallel time method for words, nonlinear, degenerate, and periodic parabolic problems. So we will again see some cyclical structure, but now it's not, it's already encoded into the problem and not that we use the beneficial properties of it. So, how do we go about it? So first I will give you more the wrong direction.
You can point anywhere. It doesn't matter.
So first I will give a motivation about what our motivation for this class of problems. Then we will talk about a very naive method, and then we will talk about two iterative methods to solve this kind of problem. And in the end, for a big chunk, we'll talk about the numerical illustration, conclusions, outlook, and maybe an advertisement data. So motivation. So we are interested in Linz. And I forget this talk is based in joint work with Herbert Egger, who is also in Linz. So in Linz, we are currently very interested in simulating electrical machines, and the prototypical equation for time-dependent phenomena in electrical machines is the so-called magnetopartistatic approximation of Maxwell's equations, or the eddy current equation, where we have the structure that we have here, this curl part with a nonlinear material law here that gives you the magnetic properties of the material. We have, for this talk, current excitation, so impressed current density. We have some conductivity of the material, and here it's important that this conductivity can be zero. So some points of the domain you don't have conductivity. Think about electrical conductivity. Think about air. Air doesn't really conduct. Electrical conductivity. And also what we have periodic problems. So we have that this time point at the end point, sigma times this one is the same. And what are some problems that appear this? For instance, if we simulate the magnetic field inside the rotating electrical machine, this was done by a student of mine, and then they're not really interested, engineers are not really interested in just the simulation. So this is now the magnetic field, current levels of the magnetic potential. They're interested in this curve, which is the torque that over the rotation is given, and if everything is positive, we translate some power. However, what I will talk today about is something else, namely eddy current. As a problem here is a power transformer here, root mesh. And here the interest is, okay, I want to transfer power and there shouldn't be any losses. So we measure the eddy current losses, for instance, in the housing. And if I put in 1000 watts and I have a loss of 1 watt, this is okay. If I put in 1 watt, then I have a loss of 1 watt, maybe not so good idea. So we need to somehow try to simulate this and get this. And here in this example, for instance, the only region where sigma is non-zero would be the dark blue region. Everything else, it's zero. Okay, so how can we write down this as an abstract problem? So we just have some strongly monotone and Lipschitz operator K that takes part of the spatial part. Then we have our time derivative, and in front of the time derivative, we have a continuous symmetric but only non-negative operator sigma. And again, we have our continuity, our periodicity. And existence of uniqueness of this problem is well understood. So this can be established very easily with this strong monotonicity argument that just say, okay, solution exists. And you can find it, for instance, in the book by Seidler. However, this proof is based on compactness arguments, so it doesn't really give you a method to solve this problem. What would be a method to solve this problem is, okay, we first do a semi-discretization in time. So we now want to find sequence time series. We have an equidistant grid. We have a number of grid points. We define our discrete time derivative like this. And now in order to make sense for the first time step of the expression, we have to require some of this periodicity. How do we solve this? I mean, the first idea would be just do time stepping. Okay, where do, for instance, we do just do time stepping, solve for all this nk, and once you're done, I mean, it's pretty sure that we're not at the periodic state, so we again start time stepping with what we had before. Go on, go on, go on, until this periodic limit cycle is reached. However, do we really reach it? It's a question. The realization, I mean, is inherently sequential. I don't think we need to dispute this. But it's rather easy. You can just solve your nonlinear problem in each time step, use all kinds of acceleration there. It will be very slow, and maybe we don't even reach periodic limit state, just incremental, and the increments get smaller and smaller. That really changes. An alternative method is, okay, we want to get some grasp, for instance, on these eddy current losses. And okay, we need maybe not exactly, but only a figurative number. So we could say, okay, we just don't do any time stepping. We just solve sequence of problems. We don't need to do this in, we can do this in parallel, so they don't talk to each other. And then by maybe some knowledge, we can then post-process the time-dependent effects. And the solve step can be done entirely in parallel, because there's no time dependence here. And what I observed, I just write this, you get an overestimation of the eddy current losses, but if you just want to be safe, you might be satisfied. I'm not really satisfied. So maybe the challenge now should be, can we solve this nonlinear time periodic problem in a similar computational effort as this post-processing method, which is embarrassingly parallel. And let's try to do that. Okay, so we'll do this. I will do this with two iterative methods. First one is fixed point iteration. So this is our problem structure. We have here our nonlinear term and our time point, this periodicity. And now we introduce some linear and continuous operator k, and we add it on both sides of the equation. Yeah? Here, and we bring the nonlinear part over to the right hand side. And with nothing changed, but now we use this equation to define a fixed point iteration. So how do we do that? We just say we solve here for the next iterate of our fixed point iteration, and the previous iterate is inserted in the right hand side. And again, we have this periodicity. This can be then just written as if you put everything in a vector. You have this implicitly defined fixed point map phi, where in order to get the next iterate, you solve this problem. Now we have this magic k hat. How do we choose it? Important, maybe it should be time independent. So it should be the same for all time steps, and it has to be sufficiently large. For instance, what you can do if you have the heat equation, you take some piecewise constant coefficient obtained, for instance, by averaging, and then you can show that, okay, this fixed point map is contractive, it converges, and what's nice is the convergence rate is independent of the time step. However, it's still linear, so it can be very slow. What is now the structure of the linear problem? We have seen this twice already today, or 3 times if you were in the first session. We have this structure here, so this circulant matrix structure, and the right hand side is now a bit tilted maybe. So this can be either by some frequency domain, can be discretized. Again, in this block structure in the frequency space, you solve it and then come back to the time domain, or just apply something here, a parallel in time method to this periodic problem. Indeed, for instance, we will later do a multigrid in time, which perfectly fits in the theory, can be applied in parallel. Okay, and also this idea of using its frequency domains, engineers already did this 8 years ago. Okay, and the other way would be, okay, we have a nonlinear problem. We have this big all-at-once system. We just apply Newton's method directly. It's a nonlinear problem. Why not? So how would this look like? This was also applied in engineering context for electrical machines, although already 13 years ago. We have, again, our abstract Newton iterate. Next iterate is Newton plus Newton update at previous iterate plus update, and we have some step size control, maybe by mu backtracking or something like that. And how does the nonlinear system look like? Almost similar to before, but now again have here the Newton system, we need the derivative, and on the right hand side the residual. And now the structure is no longer this time invariant structure. It's still linear, it's still time periodic, but no longer time invariant because the U now lives on the diagonal of each. Okay, so we cannot really use diagonalization directly. However, we can still solve this problem by some parallel in time algorithm. For instance, any of those that we have here. I'm not sure if those kind of systems are covered by all of them in the theory, but we can at least try to apply it. And also for the whole Newton, to my knowledge, there is not really any globalization result for this all at once Newton system. Okay, so let's already come to the numerical illustration. So in order to not have to deal with H curl, we go to 2D and just do a two-dimensional problem. There we still have the curl, but it's almost the same as the heat equation. The same, just different signs. And we solve now for the z component of the vector potential. This gives you a scalar equation. We now are in a 2D plane. And what are our fields? We have a cosinus excitation. We have this here with some current amplitude that we will define later. Our conductivity is piecewise constant. So it will be 0 in a large part of the domain, high value, for instance, in housing. And then the nonlinear material law, usually you can get this from some measurements, the so-called pH curve, in order to have everything analytic. And so there is a model, so-called Brouwer's model, that fits somehow this behavior between magnetic field and H and B. In order, since here we have an exponential, if S grows and grows and grows, I mean, explodes, so we cap it at the relativity of free space. Okay, so what is our domain? Our domain is the cross-section of this transformer you saw earlier. It has the following parameters. So in the steel cage, we have the only part where we have conductivity. It's 10 to the 7. It's 0 everywhere else. It has some parameters where I fitted the H curve. Then we have the iron core, which is also a nonlinear material. In the windings, we have this current excitation, which is into the 4 moderate excitation. And there we have linear material and also air linear material. I took this benchmark from this paper. Okay, what did I use for discretization? So I used the Courant element space, so simplest case, and the dimension will be denoted by NV. In time, I just used the implicit Euler method, which we already had the whole talk. And here n is now the number of time steps, and we have a constant time step size for the time being. And we will compare these solution strategies. So first we will do these fixed point iterations, and this linear system, this linear time invariant system, are solved by a multigrid in time. So applying multigrid directly to a hierarchy of time grids. Then I will use Newton's method. We do not really have any theory, but just see how it works. And there, all this linearized system again with this time multigrid. And in order to see that we ensure that we have a decay in the residual, I employ some backtracking. And then, as a comparison, how would time stepping work? And again, in each step, we have then applied Newton's method, but now much smaller system. Again, backtracking. And here the linear systems, since they're 2D problems, there is not really that big, so we can just do that. And now a very important step, namely the initialization. And here we could just start with what I in the beginning said gives you a bit of an overestimation of these eddy current losses. We just solve the sequence of, not sequence, we just solve for each time point the static problem without any time derivative. It can be done perfectly parallel, or you add some mass term, depending on what you like. How do we stop all these algorithms from before once this big space-time residual is reduced by e to the minus 4, starting with this initial guess? How was this implemented? So implementation at this time multigrid I have implemented in MFEM, it's a finite element library, and the linear solves are provided by Hypre for the time multigrid, and if I need a direct solver, I used Umspack. And I showed iteration count and runtime. Performed this on Dane in Lawrence Livermore. We have in theory 112 cores. I will not use that many. This is then what you get. So not really as exciting as maybe a rotating machine. You have here the B field, so the magnetic field, and it just, with alternating current, it just stays into this core. So these are the runtimes. So what do we have here? I used 8 MPI ranks for the fixed point iteration method and the Newton method, and I just let Umfpack figure out how many threads it needs on its own. In init, I show how much time it took to solve this decoupled static problems, which I then use an initial guess. And then you see, if you just compare these times, you see, okay, solving this is much more, I mean, and if I invest a little bit more, I get all of these temporal effects by just doing this a little bit more additional work, but I still have all of these. What you also see that somehow the time step doesn't really play a difference. So if I use 28 time steps or 512 time steps, the iteration count stays stable. There is some influence from the space, but this comes from this how to choose this k hat. It's a lot of, I don't have a systematic way, so it's just figuring out the magic number, so to say. So anyway, but you also see that if we compete against Newton's method, this one seems to have really mesh independent convergence about the same time. So maybe moving forward, it would be more interesting to get the concrete theory for this Newton's method. Still the scaling, I mean, what are the components of this algorithm? We have this residual and you have to solve the linear system. So if your method for solving the linear system has good scalability, the whole fixed point iteration will have good scalability. And here in the horizontal, so we know this is for a small spatial problem, only processes in time. Here you will see strong scaling, which is all right. I mean, this is already far too much for only 256 time steps. And in the diagonals, we can observe weak scaling, which is okay. So on this diagonal, we stay almost the same. Here in the end, we again get a little bit of a drop off in the end. But overall, I think it works out quite nice. And also in Newton's method, the solver component plays a big role. And if that one has good scaling, then this will. So you have similar numbers for Newton's method. Okay, so what are the conclusions? So we tried 3 iterative, for comparison, I did here 10 iterations with this cycling until the periodic limit cycle is happened, but it didn't converge after 10 iterations. So a lot of changes in the first 2 iterations, and then you have only tiny incremental changes, and it just stagnates. However, if you only, for instance, if you're not interested in convergence at the residual, but only convergence, for instance, in these eddy current losses, then already at 5 iterations, you already have nothing really changes at this curve, but the overall residual is still quite large. Good. Okay, so we have seen these 3 iterative methods, and fixed point iteration doesn't really depend on tau. Newton's method also somehow doesn't depend on tau, but we don't have a concrete proof for this yet. We have seen some numerical illustration. What is still to be done is, okay, this space-time Newton's method, what is the convergence, global convergence analysis? Trying this for 3D magnetoclastic, so it still works. Then, since H curl has a rather big kernel, you have to somehow fix that. So this is also, I just implemented a few methods of gauging. They all work, and also the fixed point iteration works. Newton's method work. And then what also might be interesting is not only doing multigrid in time, but as Martin Neumüller did, couple space and time together into a space-time multigrid. And also maybe in the end, announcement in my own sake. There will be at RICAM in Linz, there will be a special semester on computational methods for electric machines. But what may be more interesting for this community is the workshop 3 that I jointly organized with Ulrich Lange and Martin Gander. That will be for fast solvers of nonlinear time periodic problems. And it will be happening in November. If you want more info, you can find it on this link, or I wanted to be modern, so I also put the QR code in here. QR code in the top. And or if other, they also gives the QR code for the whole workshop. This is just our workshop where you find some more information. And there you can also find our confirmed speakers. With this, Mr. References, thank you.